Hi, in this video, I'll be talking about our work, a closer look at robustness of vision transformers to backdoor attacks. This is a work in joint collaboration with colleagues from UC Davis and University of Maryland, Baltimore County. As we are familiar by now, deep learning for computer vision has grown leaps and bounds over the years. Here we see an example of querying a large multimodal model about the breed of dog and it answers correctly. The new wave of transformer architectures have played a key role in this gold rush. Specifically, the fields of generative AI and multimodal learning have immensely benefited from large training data gathered from public sources. However, this large-scale mining can result in untrusted data sources. The field of backdoor attacks study the phenomena where the poisons introduced in training set can cause misclassification during inference when a specific trigger is present. Here we see an example of a backdoor attack wherein the model classifies correctly for the two clean images and when a specific trigger is pasted onto the image, the aeroplane is classified as dog. In this work, we discover intriguing properties related to backdoor robustness of vision transformers and compare them to standard CNNs. Here we present more details about the architectures and attacks we consider. We compare the backdoor robustness of different families of architectures, convolutional neural networks such as VGG and ResNet, self-attention based transformers such as VITs and PatchConNet, feed-forward networks such as ResMLP. We consider well-known attacks in backdoor literature such as BadNets, hidden trigger backdoor attacks or HTBA, and WNet. Triggers are of size 30 x 30 and they are pasted on a 224 x 224 image. We report the following metrics: clean model accuracy, which represents the accuracy of a model trained only with clean images; Poisson model accuracy, which represents the accuracy of a model trained with clean plus poisoned images; attack success rate or ASR, which represents the target accuracy once the trigger is pasted. For a backdoor attack to be successful, clean model accuracy should be close to Poisson model accuracy and ASR should be as high as possible. Results are averaged over 10 different source target pairs for all attacks. Here we present the results for all architectures and backdoor attacks. Breaking this table down, we find that VITs are more vulnerable than CNNs to backdoor attacks given the high ASR. ResMLP, which has different attention mechanism, shows increased robustness in comparison. We believe the difference in attention mechanism between VITs and ResMLP impact their backdoor robustness. We verify this using a control setting with two variants of VIT small transformer, the standard version with self-attention and second using a MLP sublayer similar to ResMLP architecture. We observe that the model with self-attention has significantly reduced robustness, although with a higher clean accuracy. Set of findings is related to the difference in explanation between transformers and CNNs when highlighting backdoor triggers. We find an intriguing property that when using explanation maps for the predicted category, the trigger is clearly highlighted in VITs while remaining hidden in CNNs. This is effective even when the model has not seen the trigger in training data, example in HTBA. Here we see two set of results wherein in VIT base the trigger is clearly highlighted while for ResNets the explanation is all over the image. Based on this observation, we design a simple defense. We use the explanation map to locate a small region of the image with maximum heat map. We block the corresponding region in the input to negate the trigger without changing any of the model parameters. Results where the test time blocking defense can effectively reduce attack success rate for attention based transformers with minimal impact on accuracy. We consider an aberration where we vary the blocking region since the defender has no knowledge about the size of the trigger. We observe the attack success rate after defense is lowest when blocking region is equal to the trigger size, which is 30 x 30. The ASR after defense is lower than the baseline of no defense for other blocking sizes as well. The impact on clean accuracy is minimal, leading to an effective defense strategy. The next question that arises is that how does this simple defense perform for non-patch based or invisible trigger based attacks? We find that for WANet, the explanation based blocking performs better than the random blocking based baseline without sacrificing an accuracy. To summarize, we compare backdoor robustness of well-known transformer architectures with CNNs. We find that VITs are more vulnerable compared to CNN architectures. We also find that feed-forward networks such as ResMLP are more robust. We hypothesize that the self-attention mechanism in transformer might lead to reduced robustness. We also show that explanation map for transformer highlight the trigger more distinctly compared to CNNs. This shows that transformers learn features fundamentally different compared to other architectures. Based on this observation, we design a simple defense to block the trigger using explanations. Attack success rate can also be reduced when the defender has limited knowledge about the trigger or the trigger size. We find that the blocking is effective for other types of attacks as well, example WNN. For more details or questions, please stop by our poster. Thank you.